So my name is Adam Coleman. I'm a senior consultant at Decision Lab. And today I suppose I just want to take you through a wastewater project that we've worked on recently. So it's not solely focusing on wastewater or supply chain modeling, but it's more about how we can rethink logistic networks for speed, efficiency, and resilience. So we'll look at how we took a traditional AnyLogic model from the utility sector and reimagined it using AnyLogistix. So AnyLogistix, I'll give a bit of an intro as to what it is throughout this presentation, but I'm sure most people are aware. But it's really designed for supply chain analysis. So the more important thing of this talk, I guess, is exploring how this shift from AnyLogic to AnyLogistix empowered faster insights and better decisions for us on this project. So just for a bit of background as to who we are, so we're Decision Lab. We're a decision intelligence services provider. We work across a range of different sectors, anything from defense to automotive to energy and also fast-moving consumer goods. So the list goes on. But regardless of this sector, our main focus really is to help organizations make better decisions through simulation, data science, and AI. So our work really spans across four main areas, I suppose. So research and development, training courses, bespoke tools, and specialist software such as AnyLogic and AnyLogistix. But regardless of what we're doing, the view is always to solve complex challenges in practical and measurable ways. So a common thread across all of these projects is how do we help our clients become more resilient, whether that's, like I say, in defense or if it's in supply chains. That's what today's case is really about. So kind of as previously mentioned, we work across a range of sectors and we support clients in many different techniques. But we did start out as a simulation-based decision support company where we were working with clients such as Rolls-Royce. So over time, we developed capabilities in simulation and optimization, as well as mathematical modeling. But that led us to be able to support clients in a range of different sectors, which has kind of led us to where we are today with this use case that I'm going to speak about. But this progression continued and essentially allowed us to then also develop into things like machine learning and reinforcement learning. So that is how we came to the point where we are a decision intelligence company. So I just thought I'd give a bit of a background as to what we do and why we're speaking about this use case today. So wastewater is something that's probably doesn't sound glamorous. It's pretty horrible concept, but it's a massive and highly valued sector. So as of 2024, it was valued at 9.2 billion pounds in the UK. We originally did a presentation back in 2018, which is on the AnyLogic website, where we discussed the original use case, which is what I'll speak about in a second. But back then, the value of the wastewater sector was only at 8.7 billion pounds. So I say only, so quite a lot, but you can see that in just a few years, it's already jumped by quite a bit. So this sector also produces around 16 billion tons of wastewater daily. So that provides jobs for 42,000 people. So just to give you a bit of an idea, it is a massive sector. And this isn't something that's slowing down anytime soon. There's been an emerging focus on turning waste into energy. So a lot of utility companies are investing in something called anaerobic digestion, which is where we're converting organic matter into gas and power. So that's not necessarily just for sustainability, but also as a commercial opportunity, and it can be quite a lucrative venture. So the anaerobic digestion process is what you can see highlighted in red on this diagram. So this is something that I'll go into a bit more detail in a couple of slides, but it's just to give you a bit of an idea as to how this subsystem is actually part of a greater system. So although it seems like a small aspect of the wastewater sort of logistics network, it's actually quite a crucial process. And the logistics that support this process are extremely complex. You have hundreds of different sites doing different processes. You've got regional differences in terms of the organic load. You've got digestion capacity, so we can only turn so much waste into energy. But we've also got varying energy needs up and down the country. So alongside that, we've also got new competitors emerging for these wastewater networks all the time. We have deregulation, which is forcing organizations to become more efficient and also more flexible. So if you were to think about a small delay that could happen at any of these processes in this subsystem, although it might be a small delay or a small issue, it could impact the overall subsystem and maybe even greater system on quite a big level. So, for example, if a treatment site was to close, that could mean wasted fuel, but also lost revenue and maybe even environmental penalties. So this is where the logistics aspect of it becomes mission critical. So back in 2018, we were asked to explore how a wastewater utility company that was based in the UK could improve their transport network to boost both efficiency and energy returns. So we worked alongside a company called ARUP, and in just 3 days, we were able to build a full AnyLogic simulation of the operations for the wastewater utility company. This included capturing the logic for three main facility types, which again, I'll go into in a bit more detail soon. But in this model, we had wastewater treatment works, which are highlighted in blue on the image on the right. So they're the facilities that we captured in terms of the wastewater treatment. We also had these intermediate caking facilities, which are also known as ICFs. So they're the things that are highlighted in yellow. And then we've also got last but not least is the anaerobic digesters. So one of the more important parts as well. So they are highlighted in red. So they're kind of the end point for this system. And like I said, this was just a subsystem from a much larger infrastructure. But even at this level, the interactions between these different entities are really complex. So the model that we built in AnyLogic back in 2018 included different routing types. So one of the things we wanted to look at was how the routing type impacted the KPIs that we were interested in. And if you are interested in what that is, the original use case goes into a lot more detail about those different routing algorithms. But we were also interested in understanding the trade-offs between centralizing versus decentralizing the digestion process. So we wanted to understand where they should be located, how many we needed, and so on. But we were also looking at things like the relationships between these different facilities. So how does one facility's waste become another facility's resource, and what happens throughout that entire process? But one of the most important goals throughout this wasn't necessarily just the logistics efficiency. It was also understanding how we can maximize the return on logistics and energy investments. So we were looking at things like, or KPIs like energy return on energy invested. So I guess in simple terms, are we getting more energy out than we're using to move and produce or process that waste? So if we burn more diesel or more fuel transporting this matter around than the energy that we're actually getting back out of it, then we're essentially losing money there. So this wasn't just about the operational convenience. It was about understanding whether the real value and sustainability lay within this subsystem. But this model also gave the end client powerful insights. So it was used in order to understand like all of these different KPIs that I've mentioned. But the main downside to that was that it did require a high level of simulation knowledge and expertise in order to build a bespoke model like this in AnyLogic. So that kind of led us to the next question, which was, is it possible to do this better, faster, and also make it more accessible for supply chain analysts and planners? So we wanted something that wasn't necessarily just for simulation experts who can build it using code. We wanted to understand how we could simplify this and produce that sort of greater ease of access. So this is where AnyLogistix comes into play. So as most of you are probably all aware, it's a platform specifically designed for supply chain optimization and simulation. So it has a lot of features, as Andre just demonstrated in the last conference presentation. But it does come with a lot of built-in tools that make it really easy to define things like sourcing policies or routing policies, where facilities are placed, and also carry out a range of different scenarios and experiments such as risk analysis. And I guess the main benefit here is that you don't necessarily have to know how to configure these algorithms or write the code like we did back in 2018 when we used AnyLogic. So the challenge here is, like I mentioned, could we recreate this same supply chain and same process So for the wastewater to energy process in AnyLogistix, but also in less time and still uncover similar or actionable insights. So in the AnyLogistix model, we've tried to keep it very similar or as close to the AnyLogic model as we could. So we've modeled things like the wastewater treatment works, the intermediate sites, as well as the anaerobic digesters. But we've also modeled the energy grid. So we wanted to see what the demand was over time and how that can impact these different aspects. So we've used AnyLogistix to map these supply chain nodes. We've also created the flows between these nodes to understand how the policies affect the transportation cost and all the other KPIs. But within a few hours of doing this, we had a working model. So compared to that 3 days development time of the AnyLogic model, we were able to build something very similar and give us similar insights. So the objective here wasn't necessarily to rebuild the entire wastewater treatment system. It was more just to test whether AnyLogistix could give us meaningful insights using the built-in logic that AnyLogistix provides, but also allow us to build these supply chain structures in terms of the different facilities and their behavior. So in this project, we made a deliberate choice to focus solely on transportation costs, just to get a bit of an idea as to how feasible this is. And the reason we made that decision is because in terms of energy return on energy invested, transportation is by far the largest consumer of energy investment across the network. So we thought it would be a good idea to focus on something that is important within this system in order to understand how well we can translate a model from AnyLogic to AnyLogistix. So moving organic matter between wastewater treatment plants, the intermediate caking facilities, and the anaerobic digestion sites involves a significant amount of fuel and emissions. So much more than the digestion or the processing steps themselves. So again, that's why we wanted to focus on the transportation aspect of it, because that takes up the biggest cost and is quite a big part of that logistics network. So if we're trying to maximize the net energy return of the system, or ensure that we're not burning more energy than we're producing, then transport efficiency becomes a critical lever in this process. So that's why it made sense to narrow the scope down for this project and just isolate transportation flows so that we could run what we called rapid consolidation scenarios, which I'll speak about in a second, and see how the small changes in facility locations or sourcing policies affect the overall energy and cost performance of the system. So the key message, I guess, in this use case is that we're simplifying the model to sharpen the insight. So we're not trying to avoid all of the complexity, and in future, I'm sure we could build all of that in. But this lets us test some different what-if scenarios quickly and scale up the value if that is proven to be accurate. So I'll speak a little bit about how we actually rebuilt this model in AnyLogistix before I show some of the example outputs. So I've touched on the overall process, but I'll go into it in a bit more detail now. So on the surface, the flow or the logic of the supply chain is pretty simple. You have these wastewater treatment facilities that are collecting and processing some raw organic matter. That raw organic matter is transported to what we call the intermediate caking facilities, or as I mentioned before, the ICFs. These ICFs essentially solidify that raw organic matter. So once they've carried out that process, they can pass it on to the anaerobic digesters. And that is where we actually do the conversion from the solidified or caked organic matter into usable energy. So once the anaerobic digesters have produced this energy, that is when it's passed on to the end customers or the power grids and so on. So although it seems like quite a simple process, when you scale that across dozens of geographically dispersed facilities with varying transport routes or sourcing options, different fuel costs, and also vehicle types, then the decisions you have to make become a lot more complex. So it becomes difficult to manage this in something like Excel, which is why originally AnyLogic was quite a good tool to build this, because it meant that there was less manual intervention and need for building formulas and so on. But here we wanted to, again, understand how we could translate that into an ALX model. So the first thing we did was start by building these facilities, as you can see on the map on the right. And we placed these facilities in different locations throughout Yorkshire and in England. But we also had to define the flows between these facilities. So we had to define things like shipping and sourcing policies. So that allowed us to determine which wastewater treatment works sent products to which intermediate sites, and then intermediates to anaerobic digesters and so on. But the good thing about AnyLogistix is because it provides these out-of-the-box sourcing policies, it means that we can do things like test the impact on transportation cost by changing these sourcing policies. So if we want to see how using a closest sourcing policy affects transportation costs versus the sourcing where we source from the most inventory, it's really easy to do that and run these scenarios quickly. But alongside this, we also had to account for things like transportation modes. So if our vehicles have capacities, we had to input that data into the model to understand how that adds a bottleneck on this system. But we also wanted to look at things like conversion ratios. So when we're converting from organic matter to energy, it's not necessarily a one-to-one ratio. So sometimes you don't get back exactly what you put in. And that was one of the things that we wanted to understand is, are we spending more energy than we're actually getting back? But all of that, like I said, impacts the overall efficiency and cost. So it was quite an important thing to analyze in this scenario. But with AnyLogistix, we were able to visually map the supply chain as well. So one of the things we wanted to be able to keep from the original AnyLogic model was the visualization. So as you can see on the left, we were able to visualize that supply chain. And when you look at it on the right in ALX or AnyLogistix, it's the exact same essentially. So that meant that we could quite easily recreate that GIS interface, just like we would in AnyLogic. And that gives us the same spatial understanding of the network, but without needing to build all of this animation and visualization using custom visuals. We didn't need to know any code or anything like that. It was all from using out-of-the-box functionality. So by building this model in AnyLogistix, it meant that we're able to answer sort of key strategic questions. So we haven't answered them all in the project just yet, but it could be things like what happens if we close a caking site or an intermediate site, or how would rising fuel prices shift optimal routes or change how we should source the products. Also, like what is the efficiency gain if we consolidate digestion facilities? So if we reduce them, does that actually impact something? So this approach that we took to building the model meant that because we've got a lot of the logic there already, we can easily and quickly experiment with different aspects of that supply chain, but also get visual validation through this GIS functionality. So this meant that planners and analysts can explore this network and test different scenarios without having to rebuild the model or know exactly how the underlying logic in terms of the code is working. So using this model that we built, and using all of the out-of-the-box functionality and built-in sourcing policies and so on, we were able to rapidly model the wastewater-to-energy supply chain, but also run some meaningful consolidation scenarios. So in this example, we've only focused on changing the number of ICF sites that we're using. So we wanted to understand what happens when we consolidate the ICFs and reduce the number of ICFs that we're using within the supply chain, and how does that impact the overall network. So the goal here was to reduce the transportation costs and also reduce any existing overheads that we've got. So we ran three different scenarios. The first one was the baseline, where we used the existing 16 intermediate sites. So they were producing the solidified organic matter. And we saw that in that example, we had a baseline transportation cost of £1.1 million. But in the second scenario, we decided to consolidate some of the ICFs. We got rid of the lowest performing ones, and we basically resulted in 11 sites. So in that example, we were able to see that we did reduce the transportation costs, and that only resulted in a transportation cost of £1.1 million, or 1.13 million, should I say. So this showed us that just based off the basic model that we've built so far, we could already see that we can test these scenarios and see that we've got a reduction of 0.67% in transportation costs. And although that may sound small, This is for a network that's spending millions annually on logistics. So even a sub 1% improvement means thousands in savings. So that is always the goal. And I guess the main point here is that we managed to uncover this in a couple of hours as opposed to days or weeks like we did in the original model. So what I guess is even more important here is the insight that we gained from running multiple scenarios. So we decided to kind of push it further and further. And we said, well, what if we were to consolidate this list of ICFs even further? And we reduced it down to 8 intermediate sites. And we maintained the same sourcing policies throughout this. So we always source from the closest wastewater treatments. But what we actually saw is that the further you consolidated it, the worse the transportation cost actually got. So you saw that it started to go back up again. So in this case, we saw that the transportation cost increased by 1.46% compared to the original baseline of 16 intermediate sites. So I guess the key thing here for us was that it's not necessarily just about minimizing the number of facilities that we use, but it's about finding the right balance between a fixed infrastructure cost and variable transport cost. So we wanted to essentially find that balance between cost and number of sites that we've got in terms of intermediate sites. So I think that's where AnyLogistix really excelled for us or helped us because it allowed us to explore that trade-off and avoid any sort of false optimization. So we could have looked at this and said, well, surely 8 sites is better than 11 because it reduces our overall site costs. But actually, it showed us that the transportation costs then increased. So it would have been a bit of a pointless exercise if we'd just done that in real life. So beyond this consolidation, we could test further scenarios going forwards now. So we could look at, for example, what happens if one facility goes offline? How does that impact the overall supply chain? And where should customers then source energy from, and so on? How do the rising fuel prices affect the routing decisions and the transportation cost? Or what is the impact of switching vehicle types and changing the vehicle modes that we use to deliver this organic matter? Should it be that we aim for an emission target, or do we just want to focus on transportation costs? So the core model that we've built so far would allow us to start to answer these questions, and we can just improve on that as we go. So the takeaway, I guess, here really is that resilience isn't just about redundancy, it's about the insight. So we've been able to run multiple scenarios and produce these rapid iterations to understand the differences between each one, which makes it a lot easier for supply chain teams to make confident and data-driven decisions that don't rely on weeks worth of coding or anything like that. So I guess let's just sort of take a bit of a step back now. I've spoken a lot about wastewater, but this methodology isn't just for wastewater. We've applied it to a range of different sectors already using AnyLogistix. So we've worked within the fuel distribution sectors, automotive supply chains, FMCG logistics. So very wide range of industries, but they all have their own complexities and uncertainties. So simulation and optimization is useful and it's also critical for all of those different industries. So I guess that's where AnyLogistix is really beneficial is because you can improve your resilience by testing these different disruptions. So you can run simulations to understand the impact of different events that occur within the supply chain, but you can also understand trade-offs in terms of cost versus service. So one of the things that we haven't looked at yet is when we reduce our transportation costs, are we still able to satisfy the same amount of demand? So that is quite a core thing that we need to focus on next. But we could also use this to validate decisions. So we're not just making assumptions and implementing these solutions in reality. We're actually making data-driven decisions by building these models and running these different scenarios. So this is, I guess, part of a bigger shift from reactive operations to more sort of strategical or proactive supply chain design. So I guess the last sort of point that I'll maybe make is that hopefully this has kind of given people a bit of an insight into how AnyLogistix could maybe help with supply chain modeling. So if your organization is still planning based on spreadsheets or static forecasts, then maybe now's the time to rethink and start to move towards something like AnyLogistix. So hopefully everyone's enjoyed it so far, and I know it's a pretty brief presentation, but I think we've covered most of the aspects that we needed to cover. I hope it's shown what's possible when we combine industry knowledge with smart tools like AnyLogistix and this sort of resilience first mindset. So I guess whether you're working in utilities or retail, logistics or manufacturing, these challenges that I've spoken about are universal. So I'm sure a lot of people have come across these regardless of the sector. So if this is something that you're interested in talking more about and you want to understand how you can apply these in your own domain, then feel free to reach out to us. If you've got any technical questions, feel free to reach out to myself. But if you just want to discuss support services or anything like that, then feel free to reach out to our sales email. So I guess the last question I'll pose is more for you guys to think about. So I guess what part of the supply chain is fragile or maybe siloed or maybe too slow to adapt? And what do you think it would mean to fix that in not months but days? So how could you actually benefit from that? So I guess I'll leave you with that, and that is it from me. So happy to take any questions. Okay, so I see what specific aspects of AnyLogistix make it a better choice in terms of return on investment compared to a more general simulation tool, especially for a medium-sized retailer. So I think in that case, it's more the speed that you're able to build these simulations. So like I mentioned earlier, if you're building something in like a tool like AnyLogic, it's extremely powerful and you can pretty much answer anything you need. But the downside, I guess, is that you obviously need to know how to build simulations and code and so on. So AnyLogistix allows the sort of rapid turnaround time for these solutions, which makes it a lot better for either small to medium-sized retailers or customers. I see there's a couple of other chats. So how does the found cost reduction of 0.67% compare to the accuracy of the model? Applied assumptions and approximations will lead to certain modeling error. So that's a very good point. So it's obviously something that we're keen to focus on. So this is still a work in progress. So although we've been able to replicate a lot of the functionality so far in AnyLogistix, and we've identified that we can reduce transportation costs, I think, like you say, Lex, we need to look at how accurate is this model? Are we still able to do things like achieve the same amount of service level and the lead time and so on? So that is something that we need to look at next. So it is difficult to balance the assumptions and approximations. So you mentioned AnyLogistix is designed for supply chain analysts, no coding required. Could you please be more specific on the user friendliness? Is it useful for someone who isn't a dedicated programmer but has strong supply chain knowledge? So I think that's a very good question. So in my opinion, and I'm sure a lot of people here will probably agree, AnyLogistix is very user friendly. Hopefully you saw from Andre's presentation just how user friendly it is. So you have access to all of these different tables. You can also graphically define elements on the map, which makes it a lot easier to kind of build test models and so on, and also move things around. But what I've found from delivering things like the training courses is that supply chain analysts or planners pick up AnyLogistix really quickly, and they're building models within a matter of 1 to 2 days. And I think that's just because of the nature of how AnyLogistix is designed. And then there's another question about how AnyLogistix handles seasonality. So it does actually handle that very effectively. So it's up to us to define the logic of how things change throughout the seasons and over time. So for example, we could have demand spikes near Christmas and so on. So we can build that logic into AnyLogistix by adjusting things like demand profiles or creating dynamic events that increase that demand over time. So it's really easy to build these in. But the good thing is that we also have this risk analysis experiment, which allows us to understand things like, if demand increases, will my supply chain enter a failure state? Will we maintain a steady state, and so on? And I guess last question I'll take in the Q&A is, what kind of internal resources, so IT support, data analysts, and supply chain specialists, would a retail organization need to implement and maintain AnyLogistix? So far from working with clients, we've found that they can work with AnyLogistix in very small teams. I've seen anything from a single user to upwards of 5 or 10, but you don't require a lot in terms of the users, but obviously you might need a little bit of support in terms of extracting data and so on. But